unmute that. Okay. Okay, welcome everyone back from lunch, and hopefully I'll keep your attention for 15 minutes. And it's wonderful to see everyone back in person, so I'll get started. So thank you. This is building on our ISCA 2020 paper that we presented virtually right before the pandemic started. We came out of stealth mode. We're a startup company and based in Mountain View, California. And so I'd encourage you to read through the ISCA 2020 paper as it lays out kind of the microarchitecture foundations on which the system architecture paper is based. So today I want to talk about how we take this microarchitecture and turn it into a tensor streaming multiprocessor. And this is done in collaboration with my colleagues at Groq. I want to encourage you to reach out, but this is the agenda. I want to talk a little bit about our system and the packaging hierarchy. The packaging hierarchy is an essential part to talk about because the network is packaging aware. In other words, we're going to take advantage of packaging locality. We'll talk about the network performance, describe it in terms of its topology, routing, and flow control, and talk about how we take advantage of minimal and non-minimal routes and load balance this deterministic Dragonfly network. So just taking a step back and looking at the building blocks here, that the tensor streaming processor is the chip that we built, and that contains both the compute units, the ALUs, as well as the chip-to-chip links. And you can see along the edge of the chip here, the C-to-C links, that stands for chip-to-chip. And there's 16 of those ports. Each port is roughly the Morley equivalent of 100 gig Ethernet. However, we're running our own proprietary protocol on these ports, so we're going to take advantage of that. At the heart of this, we've got a chip that uses dense SRAM at the core. You can see about half the chip is actually SRAM, and then there's large matrix multiply units on the edges of it, and all of which are driven by 144 instruction queues that we make accessible to the compiler, and the compiler is enabled to drive them directly. And that's the distinct thing about software defined. It's not about, most ISAs are about abstracting away the details of the underlying hardware. In a software defined processor, we're explicitly exposing those controls so that the compiler has direct and can exert control over the underlying hardware. So this is kind of the base unit, and we build upon this. We start with a chip, we package that chip onto a card, and on each card, this is a PCIe chem card, and there's 7 internal links that are kind of coming off the top here, and we'll see a little bit closer up here, and then 4 external links coming off the back. We package 8 of those into a node, and then we package 9 nodes into a rack, and make those accessible in the cloud. Sorry, I'm getting an echo here. Sorry, I'm getting an echo here.
Mute yourself and just turn off your speaker.
Okay, I'll turn off the speaker here.
Yeah, basically just reduce volume.
Yeah, I'm trying to. I don't have a volume control on this. Okay, there we go. Okay, sorry about that. Okay, so talking about the topology objectives, we are focused on building a low diameter network, and it's a direct network. And by direct, I mean we have a single chip that has both the communication links as well as the ALUs, and we're going to use that to build glueless multiprocessors by connecting multiples of these chips together. So there's no separate switch chip per se, or not an indirect network like a factory. We call this a software scheduled direct network. And the key here is that we have direct access. I can literally read the vector from memory and then send it to one of these chip-to-chip ports in a handful of cycles. Contrast that with a typical CPU or GPU where you're driving the network across the PCIe link or some other point-to-point link that has hundreds of nanoseconds of latency and reduced bandwidth. So this packaging hierarchy is really essential. We want to take advantage of what's commonly thought of as packaging locality, and that's the concept that things that are close together, components that are close together, can communicate cheaply and abundantly. We want to take advantage of that. One way we take advantage of that is we cram 28 cables into this chassis and then button it up with a hood so you can't see all that. But underneath the hood, that's the wire harness that's stuffed into each of these nodes. So it's very dense communication, and then we package those into a rack that we can deploy in the cloud. So a part of this is really thinking about building low diameter networks. And why low diameter? Because that gives you a low latency, low end-to-end latency, as well as low variance. Okay, so this is all about reducing the waste fraud and abuse in the network and getting your 99th percentile latency down to where you can predictably use the network. We chose Dragonfly as a topology because it's very pin efficient. We can take advantage of this bandwidth and use it very directly, build direct networks, and it's also edge and node symmetric. And we're going to take advantage of that symmetry in our reliabilities to provide reliability, an additional spare node that we can map in using a runtime system. The last reason we wanted to use Dragonfly is because it's extremely scalable. This allows us to scale up to over 10,000 processors in the system and then build that with a very low diameter, 5 hops in a maximally configured system. And Dragonfly is a hierarchical network, so there's two stages or 2 dimensions to that. A local topology, that's what I just described in the chassis. Within each node, there are 8 of them and they're fully connected. And then a global topology that interconnects all the nodes. And again, that's also fully connected. So to step back and take a look at how our communication model is very different than a traditional kind of CPU or GPU that is using RDMA. And a typical RDMA starts off by queuing some request at the source, and that request is going to cause some transactions to occur across the network. For example, you're going to send a read transaction across the network to the destination, where it will then be read from memory, and the reply will be passed across the fabric back to the original requester, and several steps later, you can use the data that you requested. We simplify this dramatically in that the sender here is that request is communicated implicitly through the compiler. In other words, we don't explicitly send a request across the network fabric. It is implicitly scheduled by the compiler. And here in this case, the compiler has omniscient information about the workload. So at the time that the data is going to be consumed, the source of that data will send the data, and the receiver will receive it in time so that it can use it directly as it's at the time it's necessary. So it observes and respects the data dependencies in the workload. We do this by providing globally synchronous communication across the network. Now, obviously, we're not building this and have a single global clock that runs around the entire 10,000 nodes. So we have a globally synchronous, the illusion of globally synchronous communication. Instead, we are building these links out of, these are plesiochronous links. And plesiochronous just means that they are synchronous within some tolerance. And that tolerance is really dictated by the clock chips that are driving them. So for example, if your clock crystal has a 50 part per billion tolerance, you're going to have some drift over time. And we have to be able to kind of compensate for that drift. So to do that, we added some instruction set support as well as hardware support. We added some hardware alignment counters, some software alignment counters, a synchronization primitive to synchronize the chips. Each chip is synchronized, and then we globally synchronize across all the chips. And we have explicit instructions that allow us to de-skew or to kind of compensate for any accumulated drift that occurs. Also, as part of this is we have to be able to gracefully handle transmission errors. And transmission errors, unfortunately, are often handled using a link layer retry, which in itself is going to insert some non-determinism, right? If you have a transmission error, it's going to replay it, and then the wheels fall off the bus. So we have to use forward error correction to give us a fixed latency across the channel. So when the sender sends a vector or sends a packet across the channel, it arrives at a fixed latency at the receiver. And that was essential in order to make the distributed system essentially extend this deterministic execution from the single chip across the entire system. So when we come out of reset, we synchronize each chip. They do this very lightweight synchronization. And then the counters are initially independent. And over time, these can drift. And so that's what these DSKU instructions are intended to do. It provides a software-based technique. It's actually a software and hardware-based technique that allows us to compensate for that drift. I just want to contrast that with conventional scale-out networks. Conventional scale-out networks use per-hop router arbitration. You typically have a distributed lookup table at every node, and that's providing the hop-by-hop routing. And it often uses a crossbar to resolve any dynamic contention. In other words, you have a bunch of packets that are arriving at input ports and they're contending for the output ports. That contention is fundamentally non-deterministic. So this is a network that is built without any arbiters. And that's a first for me, building a lot of networks at both Cray and Google. So this was interesting, building something without arbiters. Instead, to contrast that, a TSP software scheduled, there's no hardware arbitration and there's no deep input queues. We literally make the network links a functional unit that the compiler can schedule just like an ALU, just like other on-chip resources. And this allows them to load balance those links entirely in software. Just contrast that with the typical approach where you're going to pile a bunch of traffic into the network interface, hope for the best, and when you hit tree saturation and get back pressure or pause frames, anyone have a deep desire to talk about pause frames? It's a disaster, and that's what contributes to your 99% tail latency. So getting rid of all that from first principles was really a goal here, and that deterministic load balancing was essential. The other thing that we wanted to build upon is the idea that we have this concept of tensors. We don't really have messages, we have tensors, and tensors consist of one or more vectors. And our vectors here are 320 bytes, and the vector serves as our flow control unit. So literally every packet, every tensor that flows across the network has very little overhead to actually encapsulate the concept of a packet or a message. Instead, we build upon this idea of a vector and multiple vectors in time represent a tensor, and that tensor is your basic unit or message across the network. Now, the good news is we know the exact volume or size of every tensor because they have dimensions, N, H, W, and Z, right? And we can use that to help us determine how we want to load balance those links. Now, as I mentioned, a conventional network really requires, a conventional Dragonfly requires this adaptive routing in order to pick between a minimal path and a non-minimal path. In other words, you're going to prefer to start routing down a minimal path, and only when you sense the congestion, you want to switch down a non-minimal path. Unfortunately, in practice, this can lead to some bad behavior, and often you don't have complete information. You have local information that is given by the queue depths, for example, but you don't have end-to-end congestion, which is what is really necessary in order to make the correct choice. So it can lead to some undesirable performance degrading in large networks. So to illustrate this idea, I just wanted to look at the 8 TSPs within a single node. And we start with minimal routing and observe that minimal routes, there is exactly one minimal route between every source destination TSP pair. However, there's a lot of non-minimal routes. So if you look at how we can take advantage of this bisection bandwidth is to use non-minimal routing to maximize the benefit of having all these available ports, this high radix topology. Now, I want to also point out that we could have organized this as a torus, for example, and use this as a ring, but the average number of hops you would take in a ring of radix 8 would be 2. The worst case would be 4, halfway around the ring. And so even using non-minimal routes, the average is 2 and the worst case is 2. That gives us a very nice kind of solid substrate to build on. So how do we load balance the links? It's a very simple kind of rule of thumb. We want to use minimal routes when we can, when we want lowest latency, and when we have a larger tensor, and that tensor, and when we choose that is really just a function of the per length channel bandwidth, the per hop latency, and the message size. So we know the message size, and we can choose when to start routing doing non-minimal routes. And so a very simple rule of thumb
is that small tensors use minimal routes. Larger tensors, we spread them across the available non-minimal paths, just like you would do with multipathing in a fat tree. When you've got multiple uplinks to the root, you want to take your traffic pattern and spread it across as many as you can to reduce that serialization latency for the remainder for the tensor. An example of how a conventional network would apply, arbitrate and start flowing a packet, for example, from node A to node D via B. And node B might be congested and assert back pressure. And so to avoid this kind of traditional non-determinism that arises because of back pressure, we disallow it. So the hardware literally does not provide back pressure. Instead, software will pace these links. Software knows exactly how they can drive the link at near 100% efficiency and send a packet every n number of cycles to keep it at full channel bandwidth. So rather than reacting to congestion, we're avoiding congestion. And that's the key, is we want to, from first principles, not be reactive, but to avoid the congestion to begin with. And this is what allows the TSP to essentially extend that determinism across the entire distributed system. So let's take a look at performance and see how it does on both throughput and latency. So we took BERT large, which is a transformer model, and we spread it across multiple chips, and we look at the resulting throughput. And this gives you a nice example. We get literally linear scaling, and that's because as we're adding processors to the network, we're also adding communication links. Okay, so for every processing element, we're also adding communication capacity. Now, if you look at how a mesh or a torus, for example, as you add processing elements to a mesh or a torus, you're going to grow with the square root, or a 2D torus, for example, is going to grow with the square root. The bisection bandwidth grows with the square root of the number of nodes. So this also gets some very nice properties and benefits from the latency. And you can see the latency distribution. The compiler emits the code, and it tells you what the latency is going to be before you even run it. That's because the compiler has like omniscient information about the traffic pattern, with the one exception that there's a host CPU there, and you have to, the host CPU is kind of orchestrating and managing the inference. And so there's a small amount of variability across that PCIe channel, and it literally exposes itself as when that PCIe channel encounters an error, a transmission error, and it has to do its replay queue. We can't hide that, right? So we have to tolerate that latency. So the host, that host interface is kind of like our blood-brain barrier. We have to tolerate the latency variance that we see across that. But that is a very small amount of latency variance, and it's something that we can very predictably manage. And lastly, no network analysis would be complete without an all reduce. So if we look at how we do on all reduce, unfortunately, we start off here because our pin bandwidth is about 1/3 of an A100. So the comparison here is a little bit biased. So let's factor out or normalize the pin bandwidth and then compare it. So we can look at just what the topology, routing, and flow control contribute to the overall performance. And you can see one of the benefits here is if you look at this graph, it's really, the x-axis is your offered load. We're sweeping through some different tensor sizes. And this is your accepted throughput of the all reduce. So you can think of it as kind of a roofline diagram for the network. You put some in, you get some out. And this allows us to very efficiently operate on very fine-grained tensors. In other words, like I said, we're about 5 cycles away from 16 network ports. So instead of having this long latency, this long overhead to kind of get started, you can think about it as very low inertial mass. You can put your foot on the gas and drive it at full bandwidth very, very quickly. So what I hopefully motivated today was this need for synchronous global communication. Like I said, obviously we don't have a global clock that's running across the entire system. Instead, we give the illusion of a global synchronous communication fabric. And what this enables is lock-free communication across the entire system. So we use this notion of global time to give us memory consistency across the entire system. So you don't have the usual fences and barriers that go into shared memory semantics to communicate and then signal to the consumer through a lock or a mutex that data is now globally visible. it allows us to schedule the network links and directly do so in the compiler. And this, of course, allows us to load balance the links. It gives us the benefit of global adaptive routing, dynamic routing, without the complexity and overhead of it. And all of this, again, is to be able to build scalable low diameter networks, to be able to scale to 10,000, over 10,000 TSPs in the system with a diameter of 5 hops. Thank you today. I appreciate your attention, and we're hiring. So hopefully this was engaging and interesting, and hopefully you'll go to the Groq page and take a look at some of our career opportunities. Thank you.
Thank you so much for this great talk. So we'll be taking questions. If you're in the room, please come over here. We have only one microphone, so we have to share this. And if you're online, please post your questions on Hwang, and I'm going to read them out.
Hi, Dennis. Nice to see you. Great talk. So I have a question. So since this talk was more about the network, right? So even though Groq is targeting AI, do you believe these principles will apply for designing HPC networks in general?
Great question. Is this a natural convergence point for networks? I tend to think that it is. And in particular, right, do domain-specific processors really require domain-specific networks? And so Dragonfly has been a very popular network for large-scale supercomputers, and we're able to take the same principles and apply it here and get some of the benefits, but maintain determinism.
Hi, I'm Edward from Duke University. So I had a question about I see the potential and the importance of enabling asynchronous communication in a system like this, but isn't there some kind of a lost performance you get from basically you're not able to push the clock speeds as high as they can be for certain parts of the system? So did you measure any kind of performance loss from that?
Great question. So the question is, can we operate at full bandwidth? And in fact, one of the concessions that we made here early on is the external links, the long links, are using active optics cables. Those have slightly more latency to them, several cycles more latency. So we have to use essentially the longest cable and call that your fixed latency. So it adds a few nanoseconds literally to that difference. So if you accept that as an acceptable overhead to have some other sweeping and dramatic simplifications, it's a pretty good trade-off. But you're absolutely right. There is a small trade-off there.
Hello, I'm Divya from Microsoft, and thank you for the talk. So you mentioned that you can now schedule the communications through the compiler. So I was wondering, since you did an analysis for both, do you have any numbers or any specifications on how much overhead the scheduling adds compared to just running the workload with dynamic routing? Yeah.
So the question is, how much additional overhead does the static software scheduling give versus dynamic routing or dynamic hardware-based routing? We still, the compiler here is able to schedule these links with virtually there's no additional overhead. In fact, like I said, there's very shallow queues driving all of these because we're not actually tolerating the link latency across them. We don't have a retry mechanism. So it turns out it's even more efficient to offload that and do that in the compiler in the software layers where we can. And we avoid having deep queues that have to tolerate the link latency of, say, a few hundred nanoseconds.
Okay, let's take one more question.
Hey, nice talk. I have a simple question, which is that when you talked about Dragonfly topology, right? And with every Dragonfly topology node added, you're also adding a little bit more of metal bandwidth to support 2 hops and each hop thing. How well, I saw the example that was taken was with 8 nodes. How well this scales when we go to, say, 32, 64, 128, and even higher. And because the mesh and the other things that are used in normal topologies are much more scalable and better. So do you have any views on that? And while I have the mic, I have one more question. So right now I see that there's no no way for the compiler to know if anything is going to get stalled in the network. So is that true throughout? Or do you think that there might be a reason which might cause some sort of stall in it, which might be problematic?
Great question. So the first question was about scalability. Scalability in spades, we can scale up to large processor counts. And like I said, it's symmetric. So as you're adding communication, you're adding processing elements, you're also adding communication links. So you're adding network capacity as well as ALUs, right? And so the second question, I apologize, forgot what the second question was, but I'd be glad to take it offline with you. My apologies.
Let's thank the speaker once again. All right, so our next talk will be by Sahil from Georgia Tech. He's a fourth-year PhD student, and his research is on scalable hardware-software platforms for distributed ML training, network fabric design for distributed ML, and system-level optimization of distributed systems. And Sahil collaborated with Meta and Intel, and he's going to be on the job market, interested in industry positions starting from January 2023.
Thank you. Is there any problem with that? Hello, everyone. My name is Said, and thanks for attending my talk. Today I want to talk about our recent project called Themis, the Network Bandwidth Aware Collective Scheduling Policy for Distributed Training of DL models. And okay, sorry for that. To begin with, I want to give you some brief intro and motivation for this domain. When we study distributed training and training systems for ML training, we basically observe two trends. First, on the workload side, we observe that the compute and memory requirements are exponentially increasing over the years. And as you can see here, just in the course of 2 years, we see 1800x more compute requirements for doing the DNN model training. And on the other hand, on the hardware side, this right figure, you can see this shows a conceptual figure that shows that Moore's law is slowing down. And in order to keep scaling, we need to do the scaling at the on the system level. So both of these two trends actually lead us to distributed training to actually maintain the low latency for doing the training of DNN models as they grow bigger and bigger. So distributed training platforms, in recent years, we have observed that many different companies have built customized neural processing units, or NPUs in short. And they also use create their custom networks to interconnect all of these NPUs together. And examples are like Google TPU, NVIDIA DGX, or Facebook Xeon. And this trend is also growing. So when we have too many NPUs, we have to figure that out, how to connect all of these NPUs together. And because we have a large number of NPUs, we cannot connect all of them through one level of network. So for next generation distributed training platforms, it is expected that we have multiple levels of networks. We can start from having multiple NPUs within a package. And then we have package-to-package connectivity to create within a server node to create nodes. And then we have, we connect nodes together to create pods. And then the pods can be interconnected together through NICs. And you can see in each of these levels, we have a specific network with its specific bandwidth and latency characteristics. So we are, for next generation distributed training platforms, we are actually dealing with multiple network dimensions and different bandwidth and latency characteristics per each network dimension. So when we have distributed training platforms, we obviously have communication, and all reduce is one of the most dominant communication patterns observed in distributed training platforms, because any two workers that share a portion of model, they need to synchronize and synchronize their gradients to update the model. And also the all reduce is observed on some model parallel strategies. So conceptually, all reduce can be broken into two steps: reduce scatter plus all gather. And here you can see that suppose we have 3 NPUs and we want to sum these elements 1, 2, 3. All these NPUs need to sum their elements, and then each NPU needs to have a globally reduced data. So what happens is that first we do reduce scatter, which basically each NPU computes a portion of globally reduced data, and then we broadcast all of them to all other NPUs, and at the end we have all reduced that is done. So when we have a hybrid network topology with different and multiple network dimensions, what happens is that we perform all reduce hierarchically. This means that we do reduce the scatter starting from dimension 1 and all the way go to the last network dimension, and then we do the all gather in a reverse order. So in this example that we have a 2D torus, and here the rows and columns might have different bandwidths as an example. What we do is that we first do the reduce scatter across rows, then reduce scatter across columns, and then all gather on columns, and then all gather on rows. So why do we do that? The reason is that in hierarchical all reduce, network traffic decreases as we go to the next network dimension. And this is a nice property, because we know that next network dimensions typically have lower bandwidth. So it is somehow a topology aware kind of executing all reduce. But hierarchical all reduce comes with its own challenges. Why? Because so in order to utilize all of these network dimensions, we break the all reduce into multiple chunks, and then feed these chunks into the reduce scatter and all gather pipeline stages that I just gave you an example in previous slides, in order to utilize all of these different network dimensions. And since we have multiple stages, we might have different stage latencies because first we have, due to the nature of hierarchical all reduce, these chunks as they go to the next stage, their sizes change. And also we have hybrid network, which basically means that each network dimension has its own bandwidth latency characteristics. And this basically is a major problem for next-gen platforms. Why? Because we have more network dimensions, and also we can have high bandwidth across all of these network dimensions. And what we observe is that once we modeled next-gen platforms using the current trends, we observe that if we are doing all reduce in a baseline manner, we only can utilize the network bandwidth with only 56% of utilization. So here I want to just I want to show the problem, and also show how we tackle to mitigate this problem. So suppose that we have again a 2D torus here, and we have different bandwidth across rows and columns here, and we have a 64 MB chunk of data that we want to do on reduce. So the way that we do all reduce is that we start from the rows, the dimension 1, and we do reduce scatter. Then we do reduce scatter on second dimension, that is columns. Then we do the all gather again on dimension 2, And then we do all gather again back on dimension 1, which is rows. And on the right, you can see the timeline, and you can see that we have different stage latencies because of the hybrid network and also variable chunk sizes as they go to the next stage. And one thing that you can notice here is that if we want to utilize all of these network dimensions at the same time, what we need to do is that we need to pipeline across multiple of these chunks. So basically, we need to pipelining to utilize all of these dimensions at the same time. And this figure basically shows the pipelining when we have 4 chunks of all reduced. They are in different colors. But one thing that you can notice is that one of these network dimensions has too many idle times. And this is because of the load imbalance across these 2 network dimensions. Why we do observe load imbalance? So first, as I described earlier, we have hybrid network bandwidth across these different network dimensions. And then second, we have variable chunk sizes. That is a constraint of the hierarchical or reduced algorithm. And lastly, we have a static scheduling of chunks. Basically, each chunk starts from the first level and goes all the way to the last level, and we have a constant schedule. And what we observed was that this constant scheduling is basically the problem, and we can do more efficient on the third point. So what is the idea here? The idea is that there is no explicit dependency on the order of dimensions that each chunk can traverse to finish the reduced scatter and all gather chain steps. The only synchronization points is that each chunk can independently visit different network dimensions, and for doing reduced scatter stages. And once it is done, it can do all gather in any arbitrary order to finish the all gathers. And after that, basically the all reduce is finished. So the solution that we propose is that instead of giving all chunks the same static schedule, just give different schedules to different chunks to fill the idle times. And we have proposed an algorithm called Themis, which is the details is in the paper. And it works not only for all reduce, but also for reduced scatter and all gather collectives. And this one shows the previous example, but with Themis scheduling. And one thing that you can notice here is that this yellow chunk starts from the second dimensions and then go back to the first dimensions, and then again finishes at the last dimension. And by sort of rescheduling these chunks, we can maintain the balance between 2 different network dimensions. And here, this fact is highlighted that Themis gives different schedules to different chunks to basically load balance across all different network dimensions. And this is the key point of Themis, as I mentioned, that works based on dynamic scheduling. Now, I want to go to the methodology and present you some results. These are just some subset of the results that we have in the paper, and you can find more detailed results and explanation in the paper. But we targeted the workloads like single RDS microbenchmarks and also end-to-end training workloads from different domains like ResNet, DLRM, GNMT, and Transformer 1 trillion. And we targeted the multiple 2D, 3D, and 4D network topologies. And each system here in our modeling consists of 1K NPUs. And we also use the Astra simulation platform that is for simulating the distributed training platforms. And this figure basically shows where Themis sits in this hardware software stack. We have the workload layer that is the DNN training workload. It issues some collectives. And then on the communication library sits the Themis scheduler, which basically schedules these chunks appropriately on different network dimensions here. So the first set of results are basically the micro benchmarks. And here each column basically shows a different type of network topology. The first column is 2D, and this one is 3D, and the third column is a 4D sample 4D topology. And the blue dots here on the upper figure basically is the baseline runtime for a single all reduced size, and the x-axis is the all reduced size. And the orange one basically shows what happens and the runtime when we apply a Themis scheduler. And the bottom part basically shows the overall network bandwidth utilizations across all network dimensions. And one thing you can see here again is that Themis achieves near 100% bandwidth utilizations here. So to conclude, on average, we observe that we can, for some sample next generation platforms, we can speed up the micro benchmark all reduces by 1.72x, and this and also this is because we can achieve 95% of total bandwidth utilizations on average. That compared to the 56% of the baseline. And this one basically shows the end-to-end training time for different workloads. Here again, each column is a different topology, and each row basically is a different DNN workload, DNN training workload. And with the blue and orange colors basically are the compute components of the overall end-to-end training time, and yellow and green, green and red colors are basically the communication components of the end-to-end training time. And you can see that applying Themis basically reduces the communication component of the end-to-end training time. And it is very close to the ideal way. If we were able to utilize 100% network bandwidth utilizations, you can see we can closely reach to the ideal scenario. So when averaging across all these topologies and workloads for our sample topologies and some sample workloads, CNN workloads that we modeled, we can reduce the end-to-end training time by 1.33x, and on max more than 2x. So what is the conclusion of this talk? Is that, and the key takeaway of this paper is that we observe that big DNN models and larger data sets basically require distributed training at a scale. And we, on the system side, we see two trends for distributed training platforms: increased number of network dimensions and also heterogeneous bandwidth and latency characteristics, which basically makes the achieving maximum network bandwidth utilization a challenging task because of these three properties of variable chunk size across the dimensions, different bandwidth latency characteristics, and also because the baseline way of collective scheduling is not efficient. And we propose Themis that tackles this third point and schedules these chunks in a way that maintains the load balance across all these three network dimensions, or any number of network dimensions that the topology has. So in short, Themis enables system designers to basically design hybrid networks with respect to their own constraints like cost and price without worrying how to efficiently utilize the full bandwidth. So it enables the network designers to basically consider broader range of these design points for designing networks, while it ensures that it can utilize near full bandwidth. So with that, I want to thank you, and I'm ready to take questions.
Thank you so much for the great talk. As before, please step up to the front of the room to ask questions in person. And for everyone on the live feed, please post your questions on Hoover.
Hi, I'm Mark from Meta in Stanford. I love your talk and your work on AstroSim. So I have two quick questions. First, can you elaborate a bit more what you mean by dynamic? So for example, how do you handle contention or packet drops that you don't know will happen in the future? And second question is, you talk about model parallelism in evaluation. How do you perform on all-to-all in this case?
So thanks for your questions. So first of all, regarding the network traffic, basically the what we propose here is that we do not change the kind of baseline reduce scatter or all gather algorithm that is performed on each dimension. So it is still up to the communication libraries such as Nickel or any other implementation to find the optimized way of doing reduce scatter for any specific network dimension. For example, if the first dimension is ring, then you probably use a ring-based reduce scatter or all gather. And these kind of optimized algorithms basically try to minimize the contention from that perspective. And what you can do is that, and one of the parameters that is fed to Themis is just these average network characteristics that you observe and the effective latency and bandwidth characteristic of each network dimension you can give fed as a parameter to Themis, and based on that it figures that out that what should be the schedule for performing and scheduling these chunks across different network dimensions. And regarding your second question, can you just oh, okay, yeah. So for all-to-all, we perform baseline all-to-all, baseline way of performing all-to-all. And there are, I think the most obvious one is that everyone just in one phase sends data to everyone else. But recently from, what we basically did in the, and it is mentioned in the paper, is that we perform direct all-to-all. So everyone just sends data to it, because all-to-all doesn't have this property of changing and varying chunk size as you go to the next stage. So there is no point in doing it hierarchical because it doesn't reduce the traffic, network traffic, compared to all reduce scatter and all gather that has this fundamental property. Oh, you're welcome.
I think we have time for maybe 2 quick questions.
Thank you for a great presentation. I am Hwang from KAIST. My question also similar to the previous question about the R2R. So as I understand that the Themis is highly optimized the R2R or reduce communication with the pipelining. So you also evaluate the Themis in the DLN. So as I think as much as the earliest time is reduced, the critical path will be the R2R communication. And then the exposed communication time, the R2R communication time will be dominant. Yes. Then in your result, the communication time reduced very much. So the Themis is still the effective with the R2R communication.
Yeah, that is basically true. If your communication is bounded by all-to-all overhead, basically, at some point, that all-to-all communication overhead becomes a dominant factor. But what we observed here was that so we modeled the 400G and 800G NICs that will be available in the near future. And using those technologies, what we observed was that the current DLRM workloads do not show too many exposed communication for the all-to-all, although that right now all-to-all is a major problem. And this is because it is bounded by the NIC bandwidth that right now in their platforms, they have like 100G or 200G in max. But for next gen, these workloads do not show too much exposed communication for all-to-all. But your point is valid. If in the future the DLRM size also increases and all-to-all becomes a problem, then yes, Themis has some may not that much improve the overall end-to-end training time.
Thanks. So I did promise 2 questions, but I think we're running a bit behind, so I will take this offline. Thank you very much. Let's thank the speakers again. And once again, Saeed Rashidi is on the job market, interested in industry positions. Thank you. All right, so our next speaker is Kevin. So Kevin Lachlan is a PhD student at the University of Michigan, researching security and reliability in hardware-software co-design.
Thank you, Martin, for the introduction. And I'm just pulling up the screen sharing here. Okay. Hi, everyone. Thank you so much for coming today. On behalf of my colleagues at oh, okay. So it should be when I did the share mode. This is what I did earlier, but swap this way. But now I don't see it. Yeah, I can do it without the notes, it's fine. But I can do it without the notes, it's fine. So we see the wrong thing. Yeah, I know. This we did this earlier. Let's do this. There we go. Cool. Okay, take two here. Hi, everyone. Thank you so much for coming today. I'm Kevin Laughlin. I'm a PhD student at the University of Michigan. And on behalf of my colleagues at the University of Michigan and Microsoft, I'll be presenting our paper on why rowhammer is not just a security problem, but something that's becoming an increasing reliability problem. So, of course, the first thing we need to understand to get the intuition on why this paper is important is because we need to understand a little bit about rowhammer, which is a circuit level disturbance by which frequent activations of the same DRAM rows can corrupt data in nearby rows. So if we look at a bank of DRAM that organizes data in rows and columns, the first thing that we need to do to read or write data in DRAM is to activate an individual row, which will load it into a row buffer. And at that point, we can actually issue reads and writes at column size offsets within the row buffer. At that point, we can issue reads or writes at column size offsets within the row buffer. However, the part that actually matters for the context of rowhammer is that we need to activate an individual row or a set of rows at rates that surpass a rowhammer threshold. So in this example, we'll say 20,000 activations within 64 milliseconds. So when we do that, we can achieve bit flips in nearby rows due to crosstalk that occurs between nearby rows. If you take one thing away from today's talk, it's that just as malicious workloads can yield dangerous activation rates that can risk bit flips, commodity workloads can do the same. And so the particular motivation for today's talk is that rowhammer thresholds are decreasing. We need fewer and fewer activations to flip bits. And so what that means is that in prior work, we've shown that carefully crafted malicious code is known to pose an increasing danger. The key contribution of this work is to say it's not just malicious code, but rather we have common non-malicious instruction sequences that are similarly yielding dangerous activation rates. And the second key contribution of this work is MOESI-prime, a protocol that mitigates this coherence-induced hammering. And why this hammering matters even in commodity workloads, even if it's mitigated by future rowhammer mitigations, is that every rowhammer mitigation proposed thus far that's provided comprehensive protection has increased performance overhead, and it rises as rowhammer susceptibility increases. So what I'm going to talk about today is some background, a little bit more on rowhammer and on CC/NUMA. I'll get into the problem of coherence-induced hammering. I'll talk about our mitigation MOESI-prime, and I'll conclude with evaluation and takeaways. I'll start with an example of the malicious hammering that I've been talking about. And one common way is that people will repeatedly flush cache lines in order to be able to bypass the caches and force repeated activations of DRAM rows. So in this example, we have one row repeatedly being flushed and then read. And if we look at that in the context of our DRAM bank, there's a nearby victim row that after we do this enough times, we can potentially get bit flips in this victim row. In the worst case, technically speaking, a DRAM access is different from a DRAM activation, but in the worst case, every access will cause an activation. And there's additional work that talks about techniques and conditions under which the vast majority of the time an access into DRAM causes a row activation. So the key piece of the puzzle now is that CC-NUMA can change this DRAM access frequency. And all we need to understand about CC-NUMA is that it's cache coherency across multiple nodes in a system, where a node could be something like a socket or in AMD, a core complex. So if we think about a traditional single node system where we just have a couple of cores on a single node, the point of coherence, or the first shared level of the memory hierarchy shared amongst all the cores in the system, is the LLC. And what this means is that coherence traffic will go to the LLC. But once we move towards, for the context of this talk, an Intel-like CC-NUMA system, the point of coherence actually changes to DRAM. And now at this point, memory coherence traffic can actually go all the way down to DRAM. In fact, each cache line is associated with one single local node. And for other nodes, we consider them remote. So if we adjust this graph for that context, and then we think about this from the point of perspective of a line that's local to this local node, we can effectively ignore DRAM1 on the right with the remote node, and now think about the point of coherence as DRAM0 from which the cache line originates. We have two scenarios to consider. One is that if a request originates on the remote node, upon an LLC miss, we see that we'll traverse the NUMA interconnect, we'll check the local LLC, and then potentially, if needed, we'll go down to DRAM. However, we have an asymmetry here, which is inherent to NUMA. We want local accesses to be fast and to not eat up a ton of bandwidth. And so in the local LLC miss, we would love to avoid this NUMA interconnect cross if we can, and instead check something else for this. And in particular, what Intel is doing currently is they have in-memory directory. So they actually use multiple directories to track different levels of coherence information. And in this case, they're tracking cache line ownership, which for the purposes of this talk can basically be thought of as the dirty status of a line. So we would like to know, is a core's copy of a line modified or invalid, so on and so forth. So like I said, there are separate directories to track local and remote ownership. And if we return to our diagram from before, the LLC level directory tracks local node ownership, or traditional node ownership, as in the single node systems that we all know and love. And then the in-memory directory provides information about the remote coherence status of that node. And an important insight on this that will come up later in the talk is that this memory directory state is only meaningful if the local node isn't the owner. Because if the local node is the owner, the LLC will be providing the information that says, hey, this line is on the local node, whereas we will only actually use this memory directory information if we've inherently missed in this LLC directory. How Intel actually implements this memory directory is that rather than putting a portion of DRAM for the memory directory and a portion of DRAM for data, every line, every 64-byte cache line in DRAM has 2 bits reserved as metadata next to it to serve as the directory bits. And while there are many directory states, or at least more than I'll talk about in today's talk, there are 2 important ones for today's talk. The first is the A state, snoop all, which means that a line might be owned, effectively dirty, on a remote node. And the second state is remote invalid, which, just like the regular invalid state, means that it's not valid on any remote nodes. So now this brings us, with our understanding of row hammer and CC-NUMA, to the problem of coherence-induced hammering. And we followed the following methodology to identify coherence-induced hammering in commodity workloads. We used an Intel dual socket Skylake server that uses a memory directory CC-NUMA system, and we used a DDR4 bus analyzer to record memory traces as we ran workloads. And a number of these workloads we ran on single node and 2 node setups, and we measured the highest activation rate observed to a single row within 64 milliseconds. And we compared that to actually a very generous row hammer threshold of 20,000 activations within a 64 millisecond. Modern thresholds are falling even lower than this. So the takeaway from this is, if you surpass this threshold, you are going more and more in trouble as DRAM gets denser and denser going forward. In the paper, we also ran additional micro benchmarks to isolate these phenomenon, and there are more details on that in the paper. So now I'm going to present what happens and how CC-NUMA increases the highest row activation rates. We're going to start by presenting data from memcached and TerraSort, two of the commodity workloads that we ran. And on the y-axis here, I'm going to present the maximum activations we saw to any single row in the workload within 64 milliseconds. In blue, I'll present multi-node CC-NUMA data, and in orange, I'll present the single node data, while red and lower will depict modern row hammer thresholds, which are worsening and therefore getting lower and lower over time. And what we see here is that the CC-NUMA scenario vastly surpasses the single node activation rate for individual workloads. And in fact, the CC-NUMA rate is actually surpassing current safe row hammer thresholds. So this actually offers the first evidence that today's row hammer mitigations are actively being engaged by commodity workloads. And the big takeaway here is that commodity workloads can produce dangerous activation rates. So of course, the question is, what and why about CC-NUMA is making them cause these dangerous activation rates? And something that's common across all of these workloads is dirty sharing, where we define this to mean cache line sharing with at least one writer. So let's consider migratory sharing of lock protected data, where this is effectively repeated writer-writer data. Some people refer to it as ping pong sharing. And basically thread A and B are both writing back and forth to a shared data variable. And something key to note about this is that migratory sharing occurs in commodity code. And we contrast this with the scenario of repeated flushing, where I don't know too much code that I've ever written, at least, that flushes and then reads a line over and over again, where I've written plenty of code that goes after lock protected data. So in fact, we identified three key sources of coherence-induced hammering. The first that I'll talk about today is redundant memory directory writes. And then the other two, I will defer to the paper in the interest of time. To understand hammering memory directory writes, I'm going to return to our migratory sharing example from before, repeated writer-writer. And I'll give us an example where we have a local writer on node A and a remote writer on node B. They'll start. Neither of them has the data cache, so their LLC directories will be invalid, and hence the memory directory will be remote invalid, since there are no valid copies on the remote nodes. The first thing that will happen is the remote writer will write, and they will obtain a modified copy of the line as a result of that write, and the memory directory needs to be updated to say snoop all, now that we have a dirty copy on a remote node. In keeping with the migratory sharing pattern, we now jump down with a local write, where at this point, we return the modified state to the local line. And something a little quirky to note here is that the snoop all state is actually retained in the memory directory here because as I mentioned earlier, the state in the LLC directory when we have a local owner supersedes the memory directory state. So we do not need to incur a memory directory update here. Now, the problem arises when we return to the remote writer. And in fact, what happens is for a puzzling reason, we incur a redundant write here in the memory directory. And the reason that we write snoop all to something that already is in the state snoop all is because the processor coherent states, modified and invalid up here, have no way of indicating to on-die caching agents that the memory directory state is already in this snoop all state. And so therefore, the node needs to conservatively assume that the memory directory is not in that state and issue this redundant write, such that as we return with a local write and repeat this pattern over and over again, we keep issuing redundant write after redundant write to DRAM and producing a hammering phenomenon. So with a hammering phenomenon in place, we'll talk about how our protocol, MOESI-prime, mitigates this phenomenon. And the key aspect of this is that the prime states that we've added help us to avoid redundant writes. Recall that the problem is that the processor cannot recognize that the memory directory is already in the snoop all state to indicate a potentially dirty remote node. So our fix is that for each conventional dirty coherent state, we're going to add prime states. And these prime states are going to be identical to their conventional counterparts, except to indicate that the memory directory is in snoop all. So if we think about the traditional modified coherent state that indicates a line is dirty and read write, and then the memory directory is in an unknown state according to conventions, we add an additional modified prime state, which provides the same semantics as modified, except to guarantee that the memory directory is in snoop all. And of note, particularly, is that the similarity of these conventional and new states allows us to easily reason about and verify the correctness of this new coherence protocol. So in action, if we return to the previous example with MOESI-prime, meaning with modified minds, modified prime, simply meaning modified and that the memory directory is in snoop_all. When we start off with a remote write, rather than entering modified, we enter modified prime to be in line with the directory being in snoop_all below. As we return with a local write where we don't need to update the memory directory, we retain this modified prime state in the hierarchy. And then furthermore, in our next step, we proceed with the remote write that beforehand was problematic for us. But as we note now, the on-die caching agents can infer that the memory directory is already in snoop_all and therefore safely omit this write. And as we repeat this pattern, the hammering phenomenon is eliminated and we no longer have redundant memory directory writes. All right, so I'm going to talk about how we evaluated MOESI-prime and some takeaways in conclusion for our paper. We ran this in Gem 5 using configurations modeled after a major cloud provider's production settings. And we compared MOESI-prime to MOESI and MESI baseline protocol implementations that were using memory directories. For the first thing we did was we ran micro benchmarks designed to induce coherence-induced hammering. And we confirmed that in the baseline protocols, these micro benchmarks did indeed induce this phenomenon, whereas in MOESI-prime, the phenomenon was mitigated. For commodity workloads, we ran Parsec 3.0 and Splash 2x multi-threaded workloads, many of which surpassed this 20,000 activation rates per 64 milliseconds on the baseline system. And we found that most crucially, we were able on average to eliminate well over 75% of the activations in the worst case scenario. And in some cases, we were even able to achieve a slight increase in execution time and DRAM power due to these unnecessary operations being omitted from DRAM traffic. So all in all, the takeaway is that MOESI-prime effectively mitigates coherence-induced hammering and can even slightly improve performance and power in systems. To recap what I've talked about today, our first key contribution is the discovery and disclosure of coherence-induced hammering, where commodity workloads can yield dangerous activation rates that pose a risk both going forward in terms of potential row hammer bit flips, as well as causing increasing performance overheads as mitigations are provided for row hammer. The second key contribution is MOESI-prime coherence protocol that actually eliminates this coherence-induced hammering in workloads. And last but not least, we encourage you to check out the paper for much, much more. I would be remiss if I didn't thank my awesome collaborators/mentors who have been an absolute pleasure to work with. And finally, I'd like to thank you for listening and take any questions.
Thank you so much for the great talk. As before, if you want to ask a question in person, please come up to the front of the room. And if you're online, please post the questions on Hoover.
Hi, thanks for the great talk. Anish from Georgia Tech. So I have a couple of questions. First is, where do the extra bits for storing the directory state in the memory come from? How is that implemented?
Hi, thank you. The memory directory bits are taken from traditional ECC state space. So there's 64 bytes per cache line, which is 512 bits. There are traditionally 64 extra bits for ECC, and instead 2 of the bits are taken for the memory directory, so that there becomes 62 extra bits for ECC.
That makes sense. And the second question is, in MOESI-prime, is the worst case behavior similar to MOESI, or are you always able to reduce the number of writes?
We found that we found that in the worst case workloads that had the maximum activation rates, we significantly reduced our activation rate compared to MOESI. So the workload in the paper to take a look at would be FaceSim. There were workloads that the reduction wasn't as significant, but overall, the worst case workloads significantly reduced from 70,000 to under 10,000.
Moin Qureshi, Georgia Tech. Very nice piece of work. I really like the attack. Do you know how many hammers were possible with other kind of attack, like flush-based attack or a prime probe attack? And if the system can handle that rate, it has mitigations to handle that rate. What implications does having one more attack vector that has like some rate, right? Like what is a practical implication given that other attacks are also possible? Thank you.
So compared, the optimal rate for hammering was from, I believe it was an S&P paper from 2020, which was basically using the memory directory and flushing. And we did not surpass that optimal rate. The significance of why it matters in spite of not exceeding that optimal rate is twofold. One, what really matters is whether you exceed the rate that is dangerous, and we do that. And second, this is the only phenomenon so far that we've observed that actually occurs in commodity workloads, and it is likely to occur even more as people move from socket CC-NUMA to chiplet CC-NUMA. And so rowhammer mitigations that might be comprehensive have been shown to have rising performance overhead as the threshold lowers. And as a result of that, we could see commodity workloads actually exhibit performance overheads.
So I think we can do one more questions, and the next speakers can set up while we do this question.
Yeah, migratory sharing with this microphone. Let's see. So Mark Hill, Microsoft in Wisconsin. I'm asking a question about Microsoft and Michigan paper, so maybe that's not fair. Can you say if there's analogs to this attack in the AMD or ARM protocols that you know about?
So the only protocols that I did thorough analysis on for this paper are Intel protocols, both for broadcast protocols and memory directory protocols for Intel. However, there is a hot chips presentation from AMD where one of the sources of coherence-induced hammering that we identified, AMD includes in the hot chips presentation as a behavior. In particular, what it is that when a remote request arrives at the local node, they will look up the local node LLC and DRAM in parallel, such that during migratory sharing, there will be a ton of unnecessary DRAM reads issued that result in hammering. However, to be fair, I haven't actually measured this on AMD hardware. I just read that presentation / paper.
Let's thank the speaker once again. So I realize we're running behind, but you'll really want to stay for this one. The speakers are Joseph and Hwang, and they're both first-year PhD students at MIT, and they're studying hardware security, and this is their first ISCA talk, so let's give them a good welcome.
Great. Thank you, everybody. So we need to unmute here, right? So Zoom can hear us? We're all good? Okay, great. Alrighty. So yeah, thanks everyone for staying out. I know it's been a long day, but welcome to Pac-Man, attacking ARM pointer authentication with speculative execution. And so my name is Joseph Ravichandran.
I'm One Techna.
We're both first years at MIT studying hardware security with Mengja Yen. And also on this project was our collaborator Jay Ling, and of course, our wonderful advisor Mengja. So what we found is in the literature, a lot of these attacks have been studied very, very thoroughly. So you've got your software attacks and you've got your hardware attacks. Both have been studied very extensively. But we found is that since these systems get to be so complicated, a lot of the times people working in software miss some things in hardware, or vice versa. Hardware people miss software things. And so we asked ourselves when building Pac-Man, what kinds of attacks might be possible if we combine these threat models to expose what might be lying between them? And so Pac-Man is our vision of a synergistic attack. So it's an attack that takes what's great about software and what's great about hardware and brings it into one by exposing the cracks in these interconnections in these threat models. And so we call Pac-Man a hardware-software co-attack. So now what does it mean to be a hardware-software co-attack? Well, we really bring three things to the table with Pac-Man. So the first is a new way of thinking about compounding threat models. So how do we bring these hardware attacks and these software attacks together? The second is a hardware bypass for ARM pointer authentication. So we'll talk about what that means and how we do it in just a minute. And the third is an attack on the real world Apple M1 SoC. So we'll walk you through that as well. And so we think our idea is actually pretty simple. And so instead of boring you guys with all the details, I'm going to start by explaining the whole thing in around a minute or so. So stay with me here. So memory corruption. This has been a big problem for the past 40 years. Lots and lots of work has been done trying to mitigate this, and yet it still remains a big problem. And so all these attacks kind of follow the same way of operating. You start with this read-write of memory. So your attacker can read and write your memory. Then they change a function pointer somewhere. It could be like a return pointer or whatever. And then they get arbitrary code execution. Now they own your system. This is a bad thing. And so the smart folks over at ARM said, hey, let's come up with a new solution in hardware to mitigate this problem. And so they introduced pointer authentication. Now, so the idea with pointer authentication is every single pointer gets a little hash that verifies it hasn't been changed. So you can think of this as like a tamper-resistant seal. And so now they've actually stopped us at that second step. So yeah, sure, you can read and write memory all you like, but you can't guess this hash, so you can't change the pointer. And so any pointer authentication bypass, not just us, but anyone that's going to bypass this, if you can forge that hash, if you can figure out what the right hash is, you can actually sidestep this protection. And so that's what we're going to do. We're going to forge these hashes. So you might be thinking, okay, that's simple. Joseph, let's just brute force it, right? Let's just try them all. Well, the problem is that when you use an incorrect hash, your kernel will actually crash. Your entire device will panic. And so that's not great for you as the attacker. And that's how pointer authentication works. So if you guess the pack wrong, instant crash. So here's our idea. We're going to sidestep these crashes by doing all our tests in speculative execution. This is where that hardware part of this synergistic attack comes in. And so we're going to do all our tests speculatively. We're never going to really run on any tests. That way we don't crash. And so here's today's agenda. We're going to start with some more background, talk a little bit about how pointer authentication works, all that stuff. We're going to do a high-level view of the attack, so walk you through kind of the ideas to pay attention to. We'll do a data attack, an instruction attack, and we'll give you guys your hard numbers that all the architects love to see. All right, so buffer overflows. You might have seen this before, but let's just run through it really quick. So in this example, we've got a buffer hanging out in memory, and then beneath it is a function pointer just somewhere else in memory, right? And maybe you forgot to use the right version of string copy, or maybe you messed up your sizes somewhere, and all of a sudden you've got an overflow. Uh-oh. So your attacker can now overwrite the function pointer. Now in traditional security models, that's it, you're owned. They can do whatever. And so let's fix this bug with pointer authentication. Let's see how this works. So this is the kind of the idea behind pointer authentication. So every single pointer on your system, hopefully these days, is 64 bits. And I don't know about you guys, but I'm not using all 64 of those bits. Maybe you guys have more memory than I do, but I only need 48, right? And so what we're going to do is we're going to take these 16 bits that are unused, and we're going to insert a cryptographic hash into them. So it stays with the pointer, and it never leaves the pointer's context. So it's right inside. You don't need a fat pointer or anything like that. And so we're going to compute this pack as a cryptographic function, taking into account the pointer itself, assaults, and some secret key. And the important idea here is that attackers cannot guess these. These are very hard to forge. And so let's look at this example again, except this time with pointer authentication turned on. And so the key insight here is you've still got that same bug. So your software is still broken in the exact same way. You've got this overflow that's happening, and you're still able to change the function pointer. But now what's happening is since the pack needs to match the pointer, and you can't guess the pack will be wrong. And since it's wrong, we're going to crash. So pointer authentication has kept us safe. How are we going to break it? So today's goal is we are going to reveal the pack for an arbitrary pointer of our choosing without ever causing any crashes. So how are we going to do that? Well, we're going to start by doing what's great about hardware attacks, and we're going to start with speculative execution. So we're going to guess a pack. More than likely, our first guess is going to be wrong, but we're going to take this guess and we're going to run it speculatively. So if we are wrong, which in all likelihood we are, we're not going to crash. And then we're going to keep doing that and keep guessing, and we're going to leak the verification results of each guess with a hardware side channel. Okay, you with me? So let's just revisit speculative execution really quickly just to kind of refresh our caches. So in this example, we got an if true, do A, else do B. And so in your traditional in-order CPU, you all learned in Intro to Computer Architecture, you're going to start with doing your branch, then you're going to run A, right? Simple. And so some very smart people had this idea. Let's actually try to speculate what's going to happen first and work on it while the branch is still running. And so in this case, we're going to pretend, or I guess speculate rather, that B is going to run while we're still working on that branch. And in this case, we'd be wrong. It should have been A. And so the processor is going to undo B, and then it's going to do A. And that's great and all, but the problem really comes into play when you realize that the processor doesn't really undo B in its entirety. Namely, any microarchitectural side effects are not undone. And so if B, for example, performed a load, the load would still be present in the cache, all right? So we're going to use side channels to transmit the verification results of a pointer. We're going to use the fact that this state is not undone to learn what happened during speculation. And we call this a Pac-Man gadget. So let's just really quickly revisit our threat model here. We got really three things. The first, obviously, you need that existing memory corruption bug. So some read-write in your program. Again, problem that's been around for 40 years and we still haven't solved it. The second is you're going to need local code execution. This is just some unprivileged code execution. And the third is you can trigger a Pac-Man gadget. All right. And so let's see how we can do this with all those little pieces into play. So we're going to take our existing memory bug and we're going to write a guess into memory. So we're going to guess the pack for the pointer we'd like to choose. Write it into memory, and then we're going to run the Pac-Man gadget. Again, this is the thing that reveals it speculatively. We're going to run the Pac-Man gadget with that guess. And now one of two things is going to happen. So if we're right, if we got that pack correct, remember that 16-bit hash, we're going to do a load and it will be present in the cache. So we'll be able to see it. Now, most times we'll be wrong. No load will happen. We'll actually see a speculative exception. We'll be able to tell that too, because it's not in the cache. So that's the overall idea. And here to tell you more about that, here's Hwang.
Thanks, Joseph. So now, as many of you know, there's two types of pointers, a data pointer and an instruction pointer. So we're going to talk about each of them in a sequence. So essentially, this is how a data gadget looks like. A data gadget is used to break a data pointer, and a data gadget consists of essentially three operations. First, there's an if condition that the attacker will train to mispredict. And inside that mispredict, so inside the shadow of the branch, there'll be two operations, a verification operation followed by a transmission operation. The verification operation will take a guess pointer with a pack and verify that pointer. And after that, the transmission operation, which is a load, will try to modulate the memory system using that verified pointer. So how does a data attack work? Well, for now, let's assume there's a correct pack for the guess pointer, the second line. In this case, the pack check will succeed. So what does that mean? It means that the upper bits of the pointer that held the pack will be cleared. So now this becomes a valid address. The verified pointer here is a valid address. And because this is a valid address, during speculation, the load will happen and modulate the memory system. Now, let's talk about the other case, when there's an incorrect pack. In this case, because the pack is incorrect, the pack check will fail. So what does that mean? It means that the upper bits of the pointer that held the pack will now become garbled. So they will have random bits. And this is an invalid address. So instead of modulating the memory system, the load will cause a speculative exception. So now we found a way to break data pointers. How about instruction pointers? Well, for an instruction pointer, you can use an instruction gadget. And an instruction gadget is very similar to a data gadget. The main difference is the third operation, the transmission operation. The transmission operation is now a call instead of a load. And because a call is also essentially a branch, the branch target buffer, or the BTB, will try to predict the location to jump to. So essentially, an instruction gadget causes a nested branch. And I won't go into the nitty-gritty details here today. I'll be happy to talk about it more offline. But essentially, to take care of the instruction gadget or the instruction gadget to work, the processor needs to implement eager squashes of nested branches. So up to now, it's all theory. It seems pretty simple. But how about an attack on real hardware? Well, we target the M1, which is the first desktop processor to implement ARM pointer authentication. And because we're one of the first researchers to target the M1, we actually came along some challenges. So I'll discuss that a little bit. The first challenge that we ran into is that there's no documentation of the microarchitectural details regarding the M1. So we had to reverse engineer it ourselves to find the side channels that we want to exploit. The second challenge that we ran into is that there is no high resolution timer available to user land instances in the M1. As many of you may know who have conducted reverse engineering experiments, you need a high resolution timer to reverse engineer. Third, the Mac OS is a very difficult system to integrate attack on, compared to something like Linux, which has been extensively explored in our community. Essentially, we really had to reinvent the wheel. But today, I won't be going into the details regarding how we overcame those challenges, and rather I'll give you a conjectured TLB hierarchy that we came up with. I want to emphasize that this is conjectured. So if you look in the middle, there's an L1 data TLB, and if in the bottom, there's an L2 TLB. So there's an L2 TLB backing the L1 data TLB. And up to now, this is not surprising to many of us here. This is as many of you may expect. And we actually use the L1 data TLB to monitor the victim's actions. But how about instruction attacks? For instruction attacks to work, we actually had to reverse engineer the instruction TLBs too. And here are the surprising findings that we found. First, we found that the L1's user instance instruction TLBs and kernel space instruction TLBs are actually separated from each other. They cannot create contention among each other. The second interesting finding that we found is that the L1 data TLB acts as a backing store to the L1 instruction TLBs. So because we target the kernel, what we actually do is we create additional contention in the kernel instruction TLBs, and so that it kicks it into the L1 data TLBs while we still continue to monitor the L1 data TLB. If this is a little confusing, the takeaway here is that we always monitor the L1 data TLB to monitor the victim's actions. So now we have set up the experiment. We have our speculative execution attack to suppress crashes, and we have our side channel, which is the L1 data TLB. Because we target the kernel, we set up the experiment by installing a kernel extension with 3 additional vulnerabilities. We insert a minimalized data pacman gadget, a minimalized instruction pacman gadget, and a memory corruption bug that we can use to perform a buffer overflow. So this is the pack oracle accuracy results of our cross-privilege attack. On the left, you'll see your data results, and on the right, you see your instruction results. And the x-axis goes from 0 to 12 because L1 data TLB is 12 ways for us. We conducted our experiments 20,000 times, where 10,000 times we use a correct pack, and 10,000 times we use an incorrect pack. And so the frequency goes from 0%, which means 0 samples, to 100%, which means 10,000 samples. In the graphs here, you'll see that depending on whether you use an incorrect pack or a correct pack, these 2 distributions are clearly distinguishable. And so we conclude that a simple statistical test can determine whether we use the correct pack or an incorrect pack. The accuracy here is actually over 99%. So I've told you about accuracy. How about speed? Under the pacman kernel extension that we installed, we find that each run takes about 2.69 milliseconds when we've trained the branch predictor 64 times. This will be likely be longer in real kernel code because the execution path is a little longer. But for now, assuming 2.69 milliseconds, this essentially means we can brute force an entire 16-bit pack in under 3 minutes. We also performed the static analysis of the XMU kernel, which is the kernel for the Mac OS. We used our Geeter scripting API to find a branch and search 32 instructions after each conditions of the branch. So we were looking for that verification operation followed by the transmission operation. And what we found is that the XMU kernel consists of 13,000 data gadgets, 41,000 instruction gadgets, and then some 55,000 pacman gadgets. So we conclude that the pacman gadgets are readily available in large code bases. And we have a lot more in the paper too, including our reverse engineering experiments, for example, jump to win attack, TLB details, CPU cache details, how you construct our timers on the M1, and many more. And with that, Joseph will briefly talk about Pacman OS.
Yeah, so thanks, Hwang. So when we were building Pacman, we realized that there's a couple of issues with doing attacks on a new system like this. Naturally, the ones that we already talked about. But we figured that doing research on Apple Silicon devices would be a very interesting use case for all of you, the members of the research community. And so what we wanted to do was build an environment designed by researchers for researchers to work on not only M1, but future Apple Silicon devices and do these kinds of experiments. And so what we created is something we call Pacman OS, which is a Rust-based execution environment that's going to drop you right into the bare metal. EL2, you do whatever you'd like. You can control any MSR you want. There's no other threads. There's no OS to mess with you. It's just you and the hardware. And so Pacman OS will be releasing very soon, and we hope you enjoy it.
And so Pacman received a lot of coverage over the recent days. And as this was one of the first projects for both me and Joseph entering grad school, we had a lot of fun working on it. And we are hoping to work a lot more on it soon, coming up. And in summary, modern systems are extremely complex. And as a result of this complexity, researchers tend to cut the large attack surface into disjoint threat models that they can reason with when they're thinking about defenses. The problem here is that Pacman is an attack that is at the intersection of 2 different threat models, or rather, Pacman is an attack that exploits the synergies between 2 threat models. With that, we have presented Pacman attacking ARM pointer authentication with speculative execution, and we will be very happy to answer some questions. Thank you.
Thank you, speakers. And it looks this microphone is now working, so this is excellent. Please come to the front of the room if you have any questions. As before, if you're online, please post your questions on Hoover.
It's a nice talk. I'm Hanijang from Azure University. So you provide 2 gadgets for different instruction pointer and data pointer, but I think it's very similar. So does M1 use different keys for instruction and data pointers?
Data pointers and instruction pointers use different keys. Yeah.
Thanks.
No problem.
Yeah, and read the paper for more information about why instructions are hard.
Hi, I'm Aiden Maycock. I work Microsoft. So the pack implementation details based on the ARM documentation suggest that you can have a pack space that's even smaller than 16 bits, making attacks like this even more likely or easier.
That's right, yeah.
So I do wonder, is going the opposite direction, in your opinion, making pack space significantly larger enough to prevent an attack like this? Because at the end of the day, you do still have brute force or even just blind guessing, but the speculative side of this will always exist unless there's some sort of speculation barrier put in place. So I guess it's more of an opinion, but do you think that that would be enough to protect against an attack like this?
Yeah, no, that's a fantastic question. And so pack really, the benefit of pack lies in the fact that it's part of defense in depth, right? Like, again, if you don't have a buffer overflow, you don't need pack, right? And so pack as a multifaceted approach to security, I think it's fantastic. More bits is obviously great, but I think also leveraging future features like stuff that's in the ARM 8.5 ISA that's coming out would be fantastic too for enforcing control flow integrity. So it's a combination of these things, right? That's going to really keep us safe in the future. Also move to Rust, everybody, please.
Thank you.
Hi, this is Yu from University of Southern California. Very nice talk, thank you. I have a similar question with the previous one. So my understanding of this is that you trying to combine this software memory corruption with this hardware this speculated based attacks, and I wondering does this mean that either of the mitigations can protect these prevent these Pac-Man attacks? And if it's not the case, is there any thoughts for providing newer version of protection against this Pac-Man to gain better to gain better profit?
You're interested in countermeasures, correct?
Okay.
Okay, so think about this. If you were to implement something like InvigitSpec, these TLB side channels would be mitigated, right? And so on the other hand, if we were to implement something like STT, you have to start taint tracking using the authentication, not the access, something like Spectre. So you have to change that. Now, regarding countermeasures of how we can try to block just Pac-Man, you can try to do pack agnostic execution. So for example, whether there's a correct pack or an incorrect pack, try to modulate the memory system so that the packer cannot differentiate between the two, right? But that also leads to a dilemma where we also have like now a meltdown vulnerability. So Pac-Man kind of raises this dilemma where we can either have a meltdown vulnerability or a Pac-Man vulnerability. And so, this is a new research direction, and we're also very interested in. Think about this.
Thank you very much.
There's more in the paper, so check out the paper.
Okay, thanks.
Hi, Nell, it's UC Santa Cruz. Is there a reason why in a non-tempered program a pack check should ever fail, whether speculatively or not? So is there a good reason?
I mean, if your program isn't tampering with pointers, there should be no reason for it to fail.
Right. So could you just fail or segfault even when the failed pack check was
you mean speculatively fail?
Yeah.
Yeah, that could happen all the time. So imagine like a speculative type confusion type attack where maybe some speculative register has a value that's treated as a pack when it shouldn't be or something like that. Totally could happen. So that's something I think we might talk about in the paper, maybe more in the paper.
All right. Thanks. Great work.
Thank you, everyone.
Thanks, everyone. And don't forget to check out our website, pacmanattack.com, and follow us on Twitter if you want to see more.
All right, there are also some questions online. So if you have any questions at a later point, just feel free to post them. Thanks, and this concludes the session. Thanks again to the speakers of all the talks. I think we had 4 great presentations, and enjoy the rest of the conference.